Okay, so let's do the second part of the example on page 427. They say the complete combustion of methyl alcohol is used to power some experimental automobiles. What is the delta H of that reaction, the enthalpy of that reaction? So I went ahead and just put it on the board already. So this is what they gave you. This is methyl alcohol. And then they wanted a complete combustion. So oxygen, carbon dioxide, and water vapor. Hey Noah, can you put up the dog, please? So I went ahead and balanced it. I'm assuming you already know how to do that. That's stuff you've already done. So we balanced it, and then I went ahead and drew out the bonds, the Lewis structures, okay? So I've got 2 of these guys, 1, 2, plus 3 of these, 1, 2, 3. And then on this side, I've got 2 of these molecules, and I've got 4 of these water molecules, okay? Now I'm gonna go ahead, I'm gonna grab my bond energies table, and I'm going to individually list each bond. Now this one's got a lot going on, so you have to make sure you make sure you pay attention and make sure you write down. If you accidentally write down just one single one of these numbers wrong, taking it from your table to your board, it's going to mess your whole problem up. So just be aware of that. So I'm going to start down here. I always start with my reactant side, and I'm going to subtract my product side. So this is my first bond I see, a carbon to a hydrogen. And also remember, it doesn't matter if it's a hydrogen to a carbon or a carbon to a hydrogen, it's the same bond, okay? So they're interchangeable. So I'm gonna find it on here. It's the first one. I've got 1, 2, 3, 4, 5, 6. So I'm gonna put 6 moles times this bond, which is 411 kilojoules per mole, onto the next one. I'm gonna add it. Now I see a carbon to an oxygen. So I've got 2 of those, 2 moles, times the carbon to an oxygen is 358. 358 kilojoules per mole. Plus, the next one is oxygen to a hydrogen. I've got 2 of them. So I'm going to put 2 moles times that oxygen to a hydrogen is 459. 459 kilojoules per mole. Then I've got 3 moles of the double bonded oxygen, which is 494. 494 kilojoules per mole. That's it on this side. Now I'm going to subtract. I'm going to draw a big subtract because I need to make sure I do all this first and then subtract the sum, because remember, these are the sum of one side and the sum of the other. So let's do this side. I've got a double bonded oxygen to carbon. I've got 1, 2, 3, 4 of them. So I've got 4 moles times the double bond oxygen to carbon, 799 kilojoules per mole. The next one, so I did this, I've got an oxygen to a hydrogen. I've got 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 moles. And then this is hydrogen to oxygen, 459 times, I'm going to put it over here, 459 kilojoules per mole. All right. Whew. So now all I have to do is multiply and add this side of the equation and this side, and then I'm going to subtract them. So if I go ahead, and all my moles are going to cancel, so I know it's going to be an energy unit. So if I do that, let's see, what is it? I'm going to end up, so I'm not going to spend time crunching that. My enthalpy, my delta H for this is going to be negative 1,286 kilojoules. Okay? Now, what did they originally ask me? They said, what is the delta H? So that's it. That's what the enthalpy is, the change in energy. Okay? So you're going to go ahead and have your hand at this. Remember, this is the second way. The first way to find the change in energy is doing an experiment. This is the second way, using bond energies, okay? we typically use bond, they're going to talk about this next, we typically use bond energies when, if you look up here, if there's no phases, like gas or liquid, if they don't have any phases in there, you have to use bond energies, okay? Or if there's one of these that's not on our next table, then you're going to have to use this method. So you're not going to have to use this method very often, okay, for our purposes in this class. All right, so I'm going to go ahead and erase this, and we're going to talk about the third way to find delta H. So there's 3 different ways. We're just going to be dealing with the 2. The third way is called Hess's law, okay? This is a much easier way. And Hess's law is going to be the basis of everything else we talk about in this module, okay? So real quick, Hess's law is named after a Russian chemist whose last name was Hess. And he talked about how enthalpy, or the change in energy, is a state function, and therefore it's independent of path. Well, what does that even mean? That's a very sciencey sounding thing. It doesn't really mean much to you unless we break it down. So let's just break it down. Let's talk about what a state function is. A state function is any quantity that depends solely on the final destination, and it doesn't matter what way they use to get there, okay? So they give you an example of going to an amusement park. Let's think about it this way, okay? You guys might be homeschooled. You guys are homeschooled. But there's, homeschool, there's public school, there's private school, there's charter schools. There's lots of different types of school, right? So there's lots of different paths. But what's your final destination? Graduation, right? That's everybody's final destination is graduation. So we would say that graduation is a state function. It doesn't matter which of those paths, it really doesn't matter which of those paths you take to get to graduation, because your final result is the same, okay? Now, some of the other factors in there might not be state functions, okay? So things like time, okay? The time that it takes you. Maybe it takes you 2 years to finish all of your high school requirements, but maybe it takes someone else 4 years. So in that instance, we would say the time that you took would not be a state function. It's different, right? Same thing with class attendance. Let's say you have a certain amount of days that you have to be in class versus somebody else who has another amount of days. That's not a state function, okay? The state function would be the graduation, right? So what Hess's law is saying is that the change in energy of a reaction is a state function. So it doesn't matter what that endpoint, it doesn't matter how you got there in your reaction, it matters what the end point is. So let's think about it this way. If I'm trying to find the enthalpy of water, so the change of energy to in a reaction with water, they give you 2 different equations. This one, 2H2O, and they give you this one. Oh. 2H2O plus O2. So they give you these 2 different reactions, okay? Both chemical reactions represent 2 different paths that you could go on to get to water, okay? But regardless of the path that you choose, which reaction you choose, the end point, the final destination, the state function, is going to be the same. This is exactly what Hess's law is telling us, okay? So how does this really help us calculate the enthalpy? Well, remember what that delta H represents. It represents the change in energy, the change in enthalpy of that reaction. So if you know the enthalpy of the substance in the equation, you can simply take the difference of the products and the reactants to get it. So if we have a standard, what this is all saying is if we have a standard way of being able to calculate and measure the substances, then we can use that to calculate the delta H for any reaction of those, regardless of how it was made. So it doesn't matter what reaction you made it for. If you have a standard, you can do it. Okay, so it turns out it's actually really hard to measure a lot of things that we're talking about. and some of the other stuff we're going to be talking about in a bit. It's hard to measure that change in energy, okay, of an individual substance, but we can use formation reactions. So think about this. If I have H and O, and I want to make water, H2O, okay? Say I'm combining these. I know they're not balanced right now. If I look at these, this is a formation reaction, right? I'm taking two elements and I'm combining it to form one product at the end, okay? We can actually do this because it turns out that elements in their elemental form, right? This is just an element and an element, or you could say, let's say we did this, okay? Same thing. This is in its elemental form. It's a homonuclear diatomic, and then this is also just an element, okay? If they're in their elemental form, it equals 0, okay? This is really helpful because that tells us that if this is 0 and this is 0, we can figure out what this is, and that's our standard then for that substance, okay? So this is how they actually get table 13.2. This is the standard enthalpies of formation, okay? And they call them enthalpies of formation because they're using formation reactions to find that enthalpy number, okay? So this is how they notate it. They call it enthalpy of formation, and then when there's a little 0, that tells you that's the standard, okay? So we can use, as long as they're in standard conditions, we can use those numbers in those tables. Chemists don't memorize all this stuff. There's no way. So they have books with all these different tables that previous chemists have done these experiments so that we can use them in other ways, okay? So keep in mind, standard conditions for this is not the same thing as STP that we talked about last time. Standard temperature and pressure, not the same thing. Standard conditions are just simply regular conditions running an experiment. So room temperature, you're looking at 25 degrees Celsius, and normal atmospheric pressure, 1 atmosphere. Okay, those are the standard conditions. You can only use this table if you're at those conditions. Most of our problems that we're doing here are going to be in standard conditions. Okay, so we're going to be using table 13.2. This is the next one down right here. Okay, so if you want to just note on there delta H, this whole table is Hess's law and it's delta H. And I would also make a notation that all the individual elements are equal to 0. So if I have a problem like this, it's going to be equal to 0. And we'll see that in just a second. All right. So this is our next. So this is delta H. This was bond energies. This is how we found it, reactants minus products. Now for this delta H, and we're also going to be doing delta S and delta G in a bit, all of these are the opposite. It's the sums of the products minus the reactants. This is mostly what you're going to be doing. So this is slightly different. This is almost all we're going to be doing for the rest of this module. Okay, products minus reactants. And then I give a little side note. The only difference is we're going to find for this one, the element form is not equal to 0. So for what we're doing right now, if you see just an element, you just put a big 0 in your equation. It's basically like it's not there. Okay, so let's see how this works. Okay, they give you a fancy equation, 13.9. You'll see it there on page 431. This is just the dumbed down version of that. Sum of products minus the sum of the reactants. So let's look at example 13.3. It says, what is the delta H of the following reaction? And then they give you this reaction. They give you 2NO gas plus O2 gas, 2NO2 gas. Now, keep in mind, I put my phases here. This is important because you have phases now, and so it's more precise. So Hess's law is more precise because it gives you the phases as opposed to the bond energies. You didn't know the phases. So this is definitely more precise because you know